So in this tutorial video on the electromagnetic spectrum, we are going to be looking at the following things. First of all, we'll be looking at uses of different parts of the electromagnetic spectrum. We'll be talking about risks of using different parts of the electromagnetic spectrum, and we'll be talking about how we measure our radiation dose and the units that we do that in. As with all the videos, remember to use the pause button and rewind if you need to. Remember to make summary notes and bring a note of any questions that you want to ask having watched the video to the next lesson. So, before we start talking about the uses of the electromagnetic spectrum, this is a great opportunity to just check that you can recall the names of the 7 different parts of the spectrum. So here are 7 boxes. Pause the video now and try and remember the names of the different parts and get them in the correct order. If you want to push yourself further, see if you can remember which end of the spectrum has a high frequency and which end of the spectrum has a low frequency, as well as which end of the spectrum has waves with the longest wavelength and which end has waves with the shortest wavelength. Press play once you're done. Great! Hopefully you've got something that looks a little bit like this. It might be that you've got gamma rays at this end instead, and that's fine as long as you've said that the gamma rays have got the high frequency and the short wavelength, and the radio waves have got the low frequency and the long wavelength. So we've got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Are 7 parts of the electromagnetic spectrum, even though in reality these boundaries are very difficult to put an exact position on. So what we have here are some suggestions of different uses of different parts of the spectrum. Take a moment and pause the video and see if you can match them up just by having an intelligent guess. So for example, which part of the electromagnetic spectrum might be used for fibre optic communications? Which part might be used for satellite communications? Pause the video and have a go at matching them up now. Let's see how you did. So, thermal imaging is used or uses infrared radiation. Security markings use ultraviolet waves. If we are looking at fibre optic communications, we're using visible light. If we are looking at TV and radio signals, we are looking at radio waves. If we're looking at satellite communications, we're looking at microwaves. And if we're looking at medical imaging and sterilising surgical equipment, we're going to be looking at X-rays and gamma rays. Now, before we go any further talking about uses and risks associated with the electromagnetic spectrum, we need to remind ourselves of a key principle about this waves topic that we've learned over and over again and seen in lots of different situations. And that's the 3 things that a wave can do at a boundary between 2 different materials. We've looked at this with light, with sound, with seismic waves. So let's just remind ourselves. If a wave reaches a boundary between 2 materials, so this is one material and this is another material, at that boundary 3 things could happen. First of all, the wave could be reflected, so it bounces off and travels back in the other direction. Or the wave might be transmitted, it might pass through the boundary into the next material. If it has been transmitted through the boundary, it might also be refracted, and you might see that the wave changes direction. Or we might find that when the wave reaches this boundary between the 2 mediums, one medium here, one medium here, the wave cannot be transmitted and it isn't reflected, and in fact it's absorbed. The energy that's being transferred by the wave is absorbed by the material. Now, the reason that we reminded ourselves about this is because one of the most one of the key points about the different parts of the electromagnetic spectrum and the different waves is that they do different things at different boundaries. So, for example, radio waves and microwaves behave differently at the boundary with the ionosphere and the atmosphere. Because they behave differently, they have different uses. X-rays behave in a certain way with soft tissue, bone and metal, so they have a specific use, unlike the other waves. Infrared waves can transmit through certain materials that visible light cannot, so it has particular uses. As you go through this page of class notes that are available on the Google Classroom, keep in mind the whole time that the key to the uses for each part of the spectrum is that they do different things in terms of reflect, transmit and absorb at different boundaries between two materials. And that's the key to understanding the whole thing. So if you go through the different examples, and we're going to go through a couple of them now, keep thinking, what is the boundary between the two materials? Is the wave being reflected, transmitted or absorbed? So if we have a little look at this mind map that we've seen in class before, it's got lots of details of different uses. There's some really interesting details on how radio waves are transmitted, some really interesting details on radio waves and microwaves and how they behave in the atmosphere, as well as X-rays and gamma rays and how they're used for imaging. So once the video is over, you will probably want to get up this page of class notes, have a little look, go through and add particular points to your summary notes. So let's look at the example of microwaves and radio waves next. Microwaves and radio waves are both parts of the electromagnetic spectrum. They're both transverse waves, but they behave in different ways when they get to the boundary with the ionosphere in the atmosphere. So, microwaves are transmitted through the boundary. However, radio waves are reflected off the boundary. This means that radio waves, because they are reflected, can transmit signals over really long distances, and this makes them very good for use with terrestrial TV and radio signals. So even though there isn't a line of sight because the Earth is curved, because of this reflection, signals can be transmitted over long distances. However, this isn't the case with microwaves. They get transmitted through this boundary, and that makes them really good at communicating signals to satellites on the other side of the boundary. So here's an example of where their different behaviour, with radio waves being reflected and microwaves being transmitted at a boundary, means that they have different uses. Let's have a look at another example of X-rays. X-rays behave differently at the boundary with soft tissues and skin and bone than visible light. X-rays are absorbed by metal and bone, but transmitted by soft tissue. If you look at your hand now, you can see that visible light is not transmitted by soft tissue. This means that we can use X-rays to give us images on photographic film of the structure of bones inside our body, which makes them really useful for medical imaging. Different parts of the spectrum do different things at different boundaries, whether it's been absorbed, transmitted or reflected. Keep this idea in mind throughout the whole topic. Now, as we're talking about X-rays, it's now time to talk about the risks and potential dangers of being exposed to too much radiation. We know that waves transfer energy, and we also know that if cells, for example, in our body absorb too much energy, this can cause damage. For example, if you burn yourself with heat, your cells have absorbed too much energy and so they become damaged. Now, the higher frequency electromagnetic waves transfer more energy than the lower frequency ones. And this leads us to a situation where X-rays and gamma rays with the highest frequency transfer the most energy, and they're actually what we call ionizing. You might have heard of this word in chemistry. If we turn an atom into an ion, in physics we say that that's because we've removed an electron. So there's enough energy in the X-rays or in the gamma rays if they're absorbed by atoms for an electron to be removed and for it to form an ion. So these rays are ionizing. Now, the problem here is that if, for example, an atom that was in your DNA absorbs ionizing radiation, that might cause your mutations within your DNA. Now, if that DNA then replicates and that cell replicates, but there are mutations in there, that can then cause health problems later down the line if they're not kept in check by your immune system, which is often the case. So it's not definitely a terrible thing if cells in your body absorb X-rays and gamma rays that are ionizing, but what it does mean is that we want to limit our exposure to X-rays and gamma rays where we can. We only want to be exposed to X-rays or gamma rays if the benefits outweigh the risks. So, for example, if you've broken your arm, potentially, the benefit of knowing that your arm is broken and receiving appropriate medical treatment is bigger than the risk posed by having one X-ray. So we have the X-ray. This is all a big continual thought process and risk assessment. What are the risks and what are the benefits? And we limit the risks as far as possible, unless the benefits, the risks from not receiving that medical image or so on would be worse than actually being exposed to that X-ray. So we want to reduce the amount of ionizing radiation that we are exposed to. And one way that we do that is by keeping track of how much we're exposed to by measuring our dose. So we're going to talk about dosage now. If we're talking about a dose of radiation, a radiation dose is a measure of the risk of harm resulting from an exposure to the body to radiation. It's a difficult thing to measure because the dose will depend on the part of your body and how much radiation and the type of radiation that you've been exposed to. So there's quite a few things that go into calculating the dose. And we don't need to be able to explain it in a lot of detail or calculate dose as part of the GCSE course. But what we do need to know is that we can measure radiation dose. It's a measure of the risk of harm resulting from an exposure. And it's measured in sieverts. And because we're talking about very small doses, most of the time, we normally talk about millisieverts in the same way that we might talk about a millimetre. We've got this milli prefix here. And that means that there are 1,000 millisieverts in one sievert. So we do need to know there's 1,000 millisieverts in one sievert, and that dosage is measured in sieverts. Now, to put this into perspective, your average dose of radiation that you will receive a year is 2 millisieverts. So we're talking about very, very tiny amounts. Some years you might be exposed to slightly more, other years slightly less. This is an average. And we're talking about risks. We're talking about not that something will definitely happen, but just mitigating and reducing the likelihood that it was. So that's radiation dose. So let's have a look and check that we've done everything we said we were going to do in the video. We've talked about uses of the different parts of the electromagnetic spectrum. And remember, we said go and have a look at the class notes from the mind map available on the Google Classroom to add some more details to your notes about different parts. We've talked about risks from different parts of the spectrum and why we want to minimise exposure. And we've talked about how we measure radiation dose in sieverts. So make sure you've got summary notes, a note of any questions you've asked, and go back and revisit any parts of the video that you think you need to look at again.